Hi, my name's Alan Federman. I am giving this talk due to the fact that I have friends at Homebrew Robotics Club who got me the job. So basically, Ralph Knock mentioned to Wayne Ramlick that Patrick Goebel was looking for someone to help part-time on this project. So pays to have good friends. So let's start with my acknowledgments. Anyway, if you've ever seen a parade of elephants, there's always a guy behind the elephants with a pail and a shovel, and that's sort of my position for this project. When parts fall off the robot, I put them back on. Because there are lots of PhDs, very brilliant people, don't know which end of the soldering iron to hold it. So seriously, today I was rewiring the robot to add a safety feature to the arm, and we'll go into that in detail. But since I'm more a hardware, sort of systems integration guy, I first want to start off with a little video of just what the robot looks like and where all the sensors are. It's a little demo and explanation about Jack. So from the top, we have a 360-degree camera, and right below that is a LiDAR. Actually, for a minute we actually saw, oh yeah, you can actually see the LiDAR going around there, blinking. Then right above the face, who is tracking me right now, we have a depth camera. And coming down to the neck, we have 5 stereo cameras vertically. Then below that is another LiDAR, you just saw him flash. And all the way at the bottom is a SICK for optical avoidance, and there's one in the back. So before that, we'll also see I have this tablet here, and it's showing some of the things it's actually tracking me and identifying objects. So you can see that I'm a person.
It's also tracking monitors and chairs.
Monitors there. And it'll protect other things like teddy bears and horses and cows. I don't know why we don't see that many here at Stanford. So we'll also quickly, here's some of the cameras, the SICK, and I don't have, we'll go into this short a little bit. It's just very well edited video. See the business end with that yellow box is the safety
Yellow
stop.
box at the very bottom is safety, and above that is a battery charger indicator.
In here, there's other cool stuff. Like right over here is a little Arduino that controls the LED, so I put that one in. And so cool. So one of the things we can do is, since it's a social robot, we can also do the arm. We can also change behaviors. So that was surprised. That was sad. Angry, gets a little red. Exterminate humans. Down to 4. A little blue. Determined. So it's amazing what adding the face adds as far as the robot interacting with people, especially when the robot's in the environment and it's actually tracking individual people. You understand that the robot knows where the people are. So the side set
one of the things that the slide set doesn't really go into is expressing intent. The robot has to express its intent when it's moving in a crowd. And we don't know how to do that
That's
yet.
my favorite. The colors really pop. And finally, embarrassed. We also have right turn. And left turn. So the idea is to communicate. We also have our arm gestures as well. Right now I'm not running the arm until I install some safety in there. So that's a tour of Jack.
So the reason why we're talking about arm safety is that's what happened to the arm in December. One of our postdocs was doing a test and the arm spasmed and basically ripped physically out of the robot. So these jagged edges are not supposed to be there. That was 2 months to repair. Fortunately, not out of my paycheck. So now we put the arm back in and there was no safety on the arm. So today, yeah.
What material is
It was like a high-strength plastic. It wasn't even carbon fiber. I'm not sure what the replacement was. I think the replacement is much stronger. But basically, it was held on by all the bolts and it just popped out.
that? Is that 3D printed or was that?
I don't think it was 3D printed,
Doesn't look like it. Looks like it's
but
molded.
I think it was some sort of casting process. But it was not a very high strength. This is a Canova arm, and I don't know, it's 24 volts, but
So the arm just did that to itself, just extending, or it ran into a wall or something?
what I understand, the arm was grabbing, it was holding on to a chair. And they were trying to do something to get the torque limiting to work, which as far as I know, we were testing it today. I basically put my hand inside the fingers and it started to press, but it did not hurt. It like quit after around 2 pounds of force. And if my finger was out, it closed the fingers all the way. So something happened, who knows? Anyway, so
Although they don't have really.
the other thing is when I put the arm back on, I made slight adjustments so it stood it was a little too close and rubbing against the shell. So I do little fixes in the mechanic.
Alan, what was the device on top of the eyes?
So on the I'll talk about that later, but we have a 3D camera, not a 3D, a 360-degree fisheye camera, a Theta, that has, basically it's 2 cameras, so it basically gives you 360 degrees, and we're using that for one of our obstacle avoidance visual tracking things. The robot is collecting data. I think the last time I looked, it was something like over 1,000 ROS topics. The ROS topic list goes on forever. Because each camera is a topic, and there are 13 cameras on the robot. So 1, 2, 10, at least 12, 12 cameras on the robot. And each one is their own topic, plus one is both an RGB and depth camera, so 13 anyway.
What type of lidars are you using?
It's using 2 Velodynes. There's one one on the head and one on the belly, so it gets coverage, so it can see, because one over here might get occluded by the arm. So,
What type of lidars are they?
so they're 2 Velodyne. I think they're
16?
16s. That's a big expense. And then there are 2 6 that are like 270 front and back. You'll actually see the data, so you can go in there. Okay. Okay, so basically what the main idea of the project is to teach robots to be polite. So, and there are a couple, right? We eventually want robots. You remember the night scope that ran over the kid, bad, and the night scope that went into the lake, bad. So these are problems we want to avoid, especially if you don't want to interact. So robots are pretty good at, avoiding, well, not perfect, not perfect, but pretty good at static obstacles. But people are kind of difficult to model. It's difficult to make a mathematical model of how a person is going to move or how a group of people are going to move. So here's an example. Person's walking the dog on a leash. The camera's not going to see the leash, the LiDAR's not going to see the leash, and the robot would have to make the interpolation that there is some relationship between the person and the dog and the leash, because you don't want to run over the leash. And right now, nobody knows how to encode that. Nobody knows how to make a rule about that. So here are some of the human environments that we want to navigate, like an airport or a terminal, people going all directions, or just a sidewalk for the last mile problem. How do you get your hot and tasty pizza from the car to the door? Amazon just bought Starship or something, didn't they? Something like that.
Dispatch.
What?
I think it was dispatch.
Dispatch, but one of those robots with 6 wheels, and they all look the same to me, sorry. So, okay, so there are 3 major elements, actually 4 major elements. Receiving humans, obviously the night scope that ran over the kid. Receiving risks, the night scope that went into the lake. And learning to navigate in a crowded environment. And then the other thing about learning to navigate is also expressing intent. So there's a 4th thing here. And so all those elements are being looked at by different, we have a fairly big team of smart people who are smarter than me, figuring out that part of it. So here's a representation of all the data that's being collected. So this is the panoramic camera, so there are 5 cameras. And the stereo on the cameras isn't very good. We're not getting good depth. So we actually have to combine the LiDAR information and the visual information to get models of people. So we're pretty good at tracking people. It's amazing, like you'll see a hand and it's per person, but it's not perfect because it really doesn't know what the range is unless the LiDAR's in. It doesn't know if it's a short person close or a tall person far. It's really funny with Patrick and me. It's like, who's on base? So the other thing, right now, you actually see the LiDAR tracks too. And besides people, it's doing other things. It's interesting because we're using something called YOLO, you only look once, which is a deep neural network. And that's happening in real time on the robot. So there's a huge honking CPU with 2 NVIDIA GPU 9000s. And that's because there's so many camera feeds coming in. And there's a lot of computation going on. We'll show more video. So one project is predicting human motion. Right? It'd be, if someone's going in this direction, hopefully they'll continue to go in that direction. So you can do a theoretical model of that. But that's probably only one way to do it. The other way is imitation learning. So one of the main focuses of the project right now is gathering data. Actually having the robot teleoperated in a crowded environment, recording everything into huge bag files, then sending the bag files to be annotated, and then finally analyzed by various computational techniques to make a neural net model of how people move. So the idea is predictability. What is people? What are a group of people doing?
What is Sophie?
Sophie is one of the algorithms that was used in one of the projects. So the other, there's a big team, and I couldn't explain the math behind it. The other thing is perceiving risks. So we have a guy on loan from Toyota, Toyota Research, Noriaki, who's working on this visual avoidance system using the theta camera, the 360-degree camera, and it's pretty cool how that works. So how that works is it actually, makes a prediction of what the next frame should look like. So if something happens where the next frame isn't what it expects it looks like, it gives it an obstacle avoidance alert. And like again, the math. But that's so easy. A 5-year-old can go out and buy a 5-year-old. So here's an example of GoNet in action. So I think what they're doing is teleoperating it, but it's giving its obstacle avoidance by figuring out what people are. This is a pretty cool demo.
That's a TurtleBot 2, isn't it?
As a TurtleBot 2, and sort of things that I do for the project, because there's a fairly big GPU in that laptop, he wasn't getting, he was only getting 10-15-minute runs. So I wired up some extra batteries to keep it going. So they think I'm a genius. Attach a battery. Don't kill them.
Oh, this looks fancy.
Like I said, they love me there, and I was like, it's like most high school students who spend a year with the first. Well, I'm also good at BSing, so that applies it too. Yeah, so it also, I don't know how it figures out that that's a drop, but it does. So, yeah, so what it's doing is actually predicting 5 frames ahead, and then if something happens that's not a prediction.
The frame
says
that
it.
was ahead of it didn't look right, so this
Yeah.
is what triggered that stop.
Yes, that's what triggers a stop.
How far apart are the frames?
I know it's less than a second. I don't know if it's a quarter second or a half second, but I think it's,
So it's just going like at 4 hertz?
I don't know that, but it's pretty fast. Right, you saw that it was able to stop from the skateboard, so.
These algorithms are mostly for indoor navigation.
Well, GoNet, we're testing it indoors, but we're running both outdoors and indoors. It's hard to run, it's been lately hard to run outdoors. Yeah, it's not waterproof and.
Or puddle proof. I mean, how
Or
does it-
puddle proof.
How do they
Oh,
distinguish a puddle from a flat surface?
That's pretty good. We don't have any, right now we don't have any way to figure out what a curve is. We were looking at we have some sonars, we had some infrared detectors, and we had a depth camera looking down. I forget which one, I think it was a Microsoft type. The Intel Sense or whatever.
Real sense?
Real sense. And that just wasn't good enough for detecting a curve. No, it was good enough to detect a curve, but the ROS node for it was in it, just didn't work. Couldn't get it to work. So I have a whole bunch of sonars that we're going to put on. But so far that hasn't been, and the thing is, if we get GoNet to work, it looks like it can detect drops. and predict that.
Which sensor was GoNet using?
GoNet was using the 360-degree
Okay.
data. And finally, we can navigate. And I'm going to show some really cool movies. So right now, I saw a couple of good demos, or a couple of good movies just today that I'll show you of the robot navigating. This is the foyer in Gates. So right now, autonomously, the robot can do go to goal. You can put ARBAs go to goal, and it will avoid people and obstacles that are not in the global map. So it can make, if we do a global map, it has a very good global map because of the LiDARs. So it knows where the walls are, and it knows where most of the permanent obstacles are. And then its local map is pretty good too, and it's pretty good at avoiding people. Okay.
Nightscope tip.
Pretty good.
Well, hey, you know. So there are two ways. One, what I said is the imitation learning, and they're doing it in a couple of ways. They're also doing it, the imitation in simulation. So we actually have a game that people can sign on to and drive the robot in a hallway and, you know,
It's asking for trouble.
avoid people, and I don't know how they reward, what the reward is,
Yeah.
right? And then they're using the same types of things for the robot navigating, for the arm to pick objects, same sort of algorithms. So it's two types. One is more like the deep neural net hierarchical solution, the other is imitation learning. And I'm going to do
When you say
that.
imitation learning, is that actually TensorFlow or is it something different?
No, imitation learning is people are driving the robot in a crowd,
Hmm.
and then the robot analyzes that data
Yeah,
and
you're
then
not using
figures.
TensorFlow.
Yeah. Okay. Oh, thank you. Patrick, me, everyone else. I'll show some movies.